Um, Hello, friends. Let us solve one problem or numerical on transcritical refrigeration system. So the problem is like this: that it is a transcritical system, and the refrigerant used is carbon dioxide, and the operating conditions are given. The operating conditions are like you have the evaporator at 30 bar, and you have the cooler, the gas cooler at say 90 bar. You're also given that this system has a capacity, refrigeration capacity of say 10 kilowatts. It means that this system is going to give you the cooling effect or refrigeration effect of 10 kilowatt at the evaporator. The temperature at the inlet of the expansion device is given as 35 degrees centigrade. So inlet temperature to expansion device means the exit temperature of the cooler. Okay, that is given to be, let us say, 35 degrees centigrade. So you know that inlet to expansion is the exit of cooler. So that temperature is given. Normally, when you do such analysis, we assume that the compressor is ideal. So when the compressor is ideal compressor, you know that that compressor does not have any friction, no friction, and there is a perfect insulation. Perfect insulation. And if that is the case, if the compression is ideal, then you know that the property of entropy does not change. So entropy remains constant. Okay, however, in real life, you know that the compressors would have certain friction. So the actual compressors would have certain friction and it is not insulated. So actual compressor would have friction and it would have heat exchange. So in that case, the entropy during compression would increase. It would not remain constant, right? So that changes the analysis, because if the compressor has a friction, then we need to understand that it has certain efficiency which is not 100%. So the isentropic efficiency is then less than 100% if there is a friction. Okay. So let us say that in this given problem, the isentropic efficiency of the compressor is given to be 70%. It means that the delta H of the compressor, which is isentropic, and delta H of the compressor across the compressor, which is actual, they are different. Okay. So that is the meaning of isentropic efficiency, delta H isentropic upon delta H actual. So if such is a problem given and you are required to calculate the performance of it, performance means what? How much electricity or how much power the compressor is going to consume, and because that is of interest, because that is ultimately going to decide your electricity bill, and of theoretical interest is how much is the coefficient of performance. So if such a practical problem is given, how do you analyze it? That we are going to discuss. Now the first thing you need to understand is, in transcritical cycle, we are talking about the region above the critical point. So if you draw a pressure enthalpy diagram for a transcritical cycle, and we are talking about carbon dioxide as a refrigerant, let us say this is your vapor dome, then we are operating partially in the supercritical region. So the component of transcritical cycle would be, there would be two heat exchangers. This is one heat exchanger for heat rejection, and there is a one heat exchanger for giving you the refrigerating effect. So this heat exchanger which gives you the refrigerating effect is the evaporator, and the heat exchanger which rejects the heat is called as a cooler. This is not a condenser, mind well. This is a cooler because you are talking about the region above the critical point. So you have two heat exchangers. One is the evaporator, other is the cooler. There is a compressor, and there is some expansion device. So this is the simple cycle. So this is a transcritical cycle, and we are talking about the refrigerant here, carbon dioxide here. Okay, so CO2 is being circulated. Now you are given that this pressure is 30 bar and this pressure is 90 bar. You are also given that this temperature is 35 degree centigrade. So let us say that you call this as the inlet 1, this is the exit 2, this is state 3, and this is state 4. So let me represent this on the pressure enthalpy diagram. This one would be your evaporator pressure. This will be your cooler pressure. Okay, now I want to locate 1. So locate 1, assuming that it is dry saturated. Whenever you are not given any condition at the outlet of the evaporator, we will have to assume that the outlet of the evaporator is dry saturated. Suppose there is a ideal compression, then it is isentropic. So that gives you a state 2. Assuming that it is ideal, the entropy remains constant. But if it is not ideal and if there is isentropic efficiency given, then you will have this as a state 2. So in order to differentiate between these two, I will call this as 2s and this is 2a. 2a is actual and 2s means isentropic. So this is compression. Then you have cooling in the cooler up to the state 3, and then there is a expansion in the expansion device. So this is 3 and this is 4. Okay. So from the pH diagram, you can easily find the enthalpy 1, H1. Okay. From the pH diagram, you can find this enthalpy H3 because you know the pressure which is 90 bar and you know the temperature which is 35 degree centigrade. So from the pH chart you can easily find H3, and that H3 has to be equal to H4 in the throttling device. Okay, so you know this enthalpy. So only enthalpy to be found is now this enthalpy H2A. So you know that if you draw an isentropic up to the cooler pressure, you get the enthalpy H2S. So H2S is obtainable from the pH chart by drawing a isentropic, and if you look at that, you will find that that value comes out to be around 480 in this problem, 480 kilojoule per kg. H1 I have got about 440 kilojoule per kg, and H3 I have got about 300 kilojoule per kg. Right? So H2S is obtained by drawing an isentropic. Now the important part is you will have to calculate H2A. So how do you find H2A? So for that we make use of the concept of isentropic efficiency, which I said is just a enthalpy difference in the ideal part, that is H2S minus H1, and enthalpy difference when the compression is actual, that is with friction, that is H2A minus H1. So from this, because some value is given here, 0.7, okay, you get to, this is known, this is known, this is known. So you can calculate this, and that comes from around 497 kilojoule per kg, or approximately 500 kilojoule per kg. Okay, so once you know this, then you can easily find the compressor work or power consumption, which is H2A minus H1. Okay, and suppose the mass flow rate is given, say it is point. Now you'll have to find the mass flow rate, then you can find the power consumption. How do you find the mass flow rate? So for finding the mass flow rate, you know that you have the capacity, refrigerating effect, and you know the enthalpy difference across the evaporator. So capacity is, let us say, in this given problem, it is 10 kilowatt. Enthalpy difference across the evaporator you can find out as H1 minus H4. H1 minus H4, that is 440 minus 300. Okay, that gives you the mass flow rate, and that comes us to be around 0.07. So this 0.07 is the mass flow rate of the refrigerant into m dot into H2A minus H1 is the power consumption. So 500 minus H1 is 440 into 0.07, that would be your power consumption, which comes to around 4.2 kilowatt. And COP, how do you find? For finding coefficient of performance, you don't require the mass flow rate, because it is simply delta H across the evaporator upon delta H across the compressor. So that if you calculate, or you can calculate it as the total refrigerating effect upon total power consumption. So I will do it this way. Total refrigerating was given to be 10 and power consumption was calculated to be 4.2. So that comes out as 2.38. So this way you can easily solve the numerical on transcritical CO2 system. I hope you understood the concept. Okay, bye for now.